My name is Winnie Sambu, and in this presentation, I will be discussing some of the findings of my ongoing PhD work in TCT under the title Measuring Child Malnutrition in South Africa, a comparison of cross-sectional and panel estimates. South Africa is a middle-income country with high levels of poverty and inequality, which manifests through high levels of malnutrition, which are relatively higher than those of other low and middle-income countries. In addition, South Africa grapples with the triple burden of malnutrition. However, the most common form of malnutrition affecting young children in the country is stunting. But recent studies show variations in stunting estimates. For my research, I used data from the National Income Dynamics Study, a panel study that collected data on household consumption, anthropometrics, and health data. NEEDS was conducted between 2008 and 2017 in 5 waves, following over 28,000 individuals and their households over time. By the last survey in 2017, the study had interviewed over 47,000 individuals. We also used data from the 2016 South African Demographic and Health Survey, which is a cross-sectional survey. However, due to time constraints, I shall only present the findings of our analysis of the NEEDS data. This presentation will therefore address 2 main aims. First, to show the trends and dynamics of malnutrition, and secondly, to assess the comparability of estimates within the NEEDS panel. To achieve these aims, we derive stunting, wasting, underweight, and overweight rates by converting anthropometric measurements to anthropometric Z-scores using the WHO child growth standards. Here, we show the trends in stunting, overweight, underweight, and wasting. We see a sharp increase in stunting between the first 2 waves of NEEDS between 2008 and 2010, followed by a sharp decline in 2012 and an even sharper decline in wave 4 in 2014. We see a similar trend in overweight rates with a sharp increase between 2008 and 2010, followed by a sharp decline between 2012 and 2014. But in the case of underweight and wasting, there are no significant variations like we observed in stunting and overweight. For the rest of this presentation, I shall focus on stunting due to the wide shifts that occur across the 5 waves of NEEDS. This figure shows the cumulative distribution function for height for age, which we use to derive stunting. You can see the wide shifts in height for age occurred across the entire distribution and were not limited to the tail ends of the distribution. This leaves us to consider whether or not these changes are real. Firstly, we consider the possibility that the significant increases in stunting in 2012 are due to the global financial crisis of 2009, because wave 2 of NEEDS occurred just after this. However, as you can see, the increase in stunting is just too large to have occurred over a 2-year period. Additional analysis, which I will not discuss here, show that there are no significant differences in under 5 population distribution across the 5 waves. So we think a more plausible explanation for the variations in stunting is that these are the effects of missing data problems or measurement errors. Our analysis of the data shows that all NEEDS waves have high levels of non-response in anthropometric data, but the prevalence of missing data is higher in very young children and in richer households. As you can see in this table, in waves 1, 2, and 3, when stunting rates are also highest, the prevalence of missing data is highest. The high levels of missing data suggest that our malnutrition estimates might be biased and leaves us with a question on whether or not these malnutrition estimates change if we reweight the data to resemble the full child sample. To deal with missing data issues, we reweight the data by generating and applying inverse probability weights to the estimates. We do this by specifying a logit regression model predicting the probability of a child having anthropometric data. We then multiply the inverse of the probability with published cross-sectional weights to generate new weights, which we refer to as the inverse probability weights. In the slide, we look at whether the inverse probability weights have any effects on demographic distributions. In table 1, as an example, columns 1 and 2, respectively, we compare the distribution of the full child sample and that of the anthropometric subsample weighted using published cross-sectional weights. As you can see, there are significant variations between columns 1 and 2, particularly in the youngest age groups. Column 3 is the distribution of the anthropometric subsample weighted using inverse probability weights, when we compare columns 1 and 3, the demographic distribution of the anthropometric subsample weighted using inverse probability weights are similar to the full child sample distributions. However, as shown in these two diagrams that compare height for age distributions based on published weights and inverse probability weights, the inverse probability weights do not have any effects on malnutrition estimates, and the wide shifts that we observed previously remain. So we can see that the missing data problem appears to be random and has no effect on the malnutrition estimates. Therefore, the more likely explanation for the wide shifts we see in stunting is measurement errors that affect the anthropometric data. In this figure, we present height for age correlative distributions for children who are part of the balance panel. These are individuals who are classified as children in all 5 waves and have anthropometric data in all 5 waves. Here, we see that the shifts in height for age are smaller between waves 1 to 3, unlike the shifts that we see in the cross-sectional estimates. However, we do observe a large shift between waves 3 and 4, which suggests a significant decline in stunting levels between these two periods. We think that this is possibly due to aging in the panel and represents catch-up growth in children who are previously stunted. In short, this graph shows more plausible shift in height for age and emphasizes our earlier presupposition of measurement errors that are affecting the full anthropometric sample in the 5 waves. Therefore, our hypothesis is that the measurement errors are likely to be wave specific and mainly occur during the initial surveys. To test this idea, we specify a pooled linear regression model estimating the effect of time, i.e. waves, on the height for age. We control for other potential correlates, including child, maternal, household, community level, and survey characteristics. Our base year of comparison is 2017, since this is the most recent wave and missing data levels are lowest. We find that compared to 2017, height for age scores are significantly lower in 2008, 2010, and 2012, even after controlling for income, child, and maternal characteristics, as well as survey characteristics. Therefore, we can conclude that the large variations in stunting are more likely the effects of unobserved measurement errors in waves 1 to 3. In conclusion, these findings indicate poor data quality. The observation is further supported when we adjust height for age measurements by subtracting the derived wave effects from the Z-scores and re-estimating stunting levels. We see a much more gradual decline in stunting compared to our original estimates. Another indicator of measurement errors is the percentage of implausible scores, which is indicative of poor data quality. When we look at the initial needs surveys, we observe very high levels of implausibility. This affects height-related Z-scores more than the weight-related Z-scores and suggests measurement errors emanate from the height measurements. In conclusion, our findings reveal that the accuracy and reliability of national level malnutrition estimates can be affected by poor data quality caused by measurement errors. Thank you.